welcome back. So, this is in this lecture we are going to talk about MATLAB model development for digital controller using difference equations. So, in this class we are going to talk about step by step custom MATLAB model development for digital controller, then digital control implementation using difference equation and the MATLAB model for digital voltage mode control. So, in fact, this is the continuation of the previous lecture where we have considered this digital voltage mode control architecture, and what we did in the previous lecture, we have considered a digital PID controller, where this PID controller we have actually considered, this is the PID controller. So, in this PID controller what we have considered, that means this G of Z, GC of Z, we have considered proportional control plus the integral control, then 1 by 1 minus Z inverse, 1 by 1 minus Z inverse plus the derivative control 1 minus Z inverse. So, this we have directly plugged in, that means we have considered one block from Simulink and Z domain block, and we have simply plugged in these values of Kp, Ki and Kd, and we have also written this transfer function in terms of polynomial of Z. Okay. Now, in this course, in this class, what we have to do? We have to write this in the difference equation, and we want to ask why do we need to do that. So, same PID controller if you take, so this is the proportional controller part, proportional part of the PID controller. So, this is like your digital PID controller, Here this part is the proportional term. So, this is the proportional, 1 minute. So, this part is the proportional term. Then this part is the integral part, and this term is the derivative, and all using difference equation. Okay, because it is a difference equation, we are talking about discrete domain. Now, the first question, what was the difficulty? We can directly plug in, this is one of the realization, because ultimately we have to realize using a controller, because when you go to a implementation, we have to implement this block. So, we cannot directly plug in this transfer function. So, that is one of the reason, and for implementation each of these is represented by a delay. So, this is a unit delay, and this delay is computed with respect to the time, that means a uniform sampling clock. Okay. So, this is what I am showing, a digital voltage mode controller, and I am going to discuss about this MATLAB model here, but this is the screenshot of the MATLAB Simulink model, and this represent our digital voltage mode controller. Now, the first thing we want to write the digital PID controller, and this can be, this is the realization using that unit delay. That means the digital PID controller can be realized using a like unit delays and also the gains. And this is the overall transfer function, and in the previous class we have plugged in this transfer function directly from a transfer function block. Okay, and where we can plug in these parameter values. Now, what is the difficulty in this direct PID controller? First of all, whenever you plugged in, let us say we are talking about a MATLAB block, and in the MATLAB if you plugged in this, that means there will be error voltage which is in discrete time, and you will get the control voltage. So, when you implement such block, let us go to the MATLAB and see our MATLAB realization. So, if we go to this MATLAB block, so I will go to the detailed block diagram. In this block, let us say if we want to plug in any transfer function, for example, we want to take it from the library. Okay. So, that we have discussed in the last class, and if we want to take one transfer function from the library. Okay, so here will be the continuous discrete. Okay, so we can take discrete time transfer function. Okay, so what we can do, we can actually, if we go to this transfer function, if we open this block, we can create this numerator and denominator coefficient. That means if we map to our this thing, so these are the coefficient. That means we can write, if you go to the previous slide, so we can write in terms of z. That means here this will be kp plus ki z by z minus 1 plus kd into, you know, what will get z minus 1 by z. And if we get the whole polynomial, then you will get some numerator polynomial of z and denominator polynomial of z. And here whatever in the MATLAB I am showing, so these are the polynomial that you have to plug in. These polynomials are in terms of, and here we have to also mention, if you go to the MATLAB block, so let us go. So here we have to also mention the sampling time. That means we have to specify the sampling time, which here we are talking about uniform sampling t, and then you plugged in the polynomial value. So now, so we can realize this using this block. That means this polynomial which will have a numerator and denominator, and you have to only provide the sampling time. Now, what is the problem here? The problem is that whenever you run a simulation, that means if you start the simulation, start your simulation, that means let us say this is the time, this is the time t, and it is a 0 time, this is 0 time, and let us say this is our total simulation time. At time t, this block will be computed. That means this block will be computed at the beginning. That means at the beginning, as if you can imagine there is a virtual clock, again the next clock virtually come like this. So that means this interval is just t. That means if you take the simulation time at t equal to 0, this block will be computed. Then at t equal to capital T, this block will be computed. Then next t equal to twice t, it will be computed. So first of all, the computation of this block will always happen with respect to clock time t, and it will start from the 0 time, that means start of the simulation. So first of all, there are two problems. One problem, you cannot use, that means you cannot use any non-uniform sampling. Non-uniform or event based sampling cannot be used. Non-uniform sampling cannot be implemented, because here in this way you cannot simply adjust the time period inside the block, because this block is fixed. So this is a fixed sampling time, so you cannot implement using this block. So this is number one. Number two, you cannot adjust the sampling instant. What does it mean? That means suppose I want sampling not exactly at that point, I want sampling here, I want sampling here. It is time t only, but I want a different instant of time. That means I want sampling which rate is t, that means sampling interval is t, it is the same, but the point of sampling I want to change, because this is necessary if you want to customize. Let us say if you go to data sheet of any A to D converter, so we need to understand that when you send the sampling clock, then it will take time to convert the data. So you should provide sufficient time for that your ADC conversion time to happen, as well as controller computation to happen, and then only you will start the clock. So there has to be a difference in the time instant between your switching clock and the sampling clock. So that means we want an adjustable sampling clock. That means where the time period may be same, it may be uniform sampling, but the point of sampling should be customizable, and this block do not allow that. Secondly, this block do not allow, so that means these two are not possible, that is the difficulty. So, you should not plug in directly this block. Then how to overcome this? And this course actually today class is dedicated for that purpose. So, instead of directly plugging the transfer function, from the library, we want to implement this transfer function using difference equation. That means, if you go back to this is a difference equation where we will use unit delay, but we still need to synchronize with certain clock. Okay, so how to do that? So, first we need a delay block. How does the delay work? So, delay means unit delay. So, that means you need to delay with respect to a clock. Now, that clock can be even a time varying clock, that means non-uniform clock, or it can be uniform clock, or that clock edges can be different, but we need just a one delay, that means between two edges of the clock. That means if I want this kind of clock, this is my T. So, this is some clock and I want to delay this signal with respect to this clock. So, that means how to do that? So, this will act like a trigger pulse, that means this pulse will be used as a trigger pulse. Whenever this trigger comes, then it will be synchronized with respect to that clock and it will create a delay of 1 unit. But the data that you are delaying, it is a vector data, it is not a 1 bit, because if you are going for digital, that means you need to convert the analog signal to digital, and then it will be either there should be some bit size, whether it is a 8-bit data, 12-bit data and so on. So, it is a vector data and the data has to be delayed by 1 unit time. So, we need to use a register, and it is because if it is a single data, then it is just simply a D flip flop. So, you define in the D flip flop, we know what happened. Whenever the clock edge comes, then only the output will take the input D, the Q will be equal to D when the edge comes. So, if such multiple like 8 such D flops are connected in parallel, then we will create an 8-bit register, okay, and all this will be common, it will have a common clock, and this is the realization. So, that means you have such clock. So, these are the 4-bit data, that means U0 to U3 are the 4-bit data, and it will generate another 4-bit delayed data, and that delay will be controlled by this trigger clock. So, we want to implement a clock based delay. So, that means now we know how to generate delay, and I will show you in the Matlab how to do that. And once you use that delay in actual realization using a register, then you have to multiply with a coefficient, because this multiplication will give you, because if you take about the PID controller, you know what we have seen, if you have that V of n, then what does the controller do? So, you need one, that means first of all it has to be multiplied with the integral gain, and this will be added with whatever is the output, that will be delayed by 1 unit, and this is the output of the integrator. So, this part they are all added, this part is ui of n minus 1. Okay. So, that means we need a scaling factor as well as we need a delay. So, now in a proportional controller, you can make this multiplication with respect to clock, because when you go to, because what will happen, this proportional gain, it is just a multiplier, but we may have to use this whole operation in synchronism with a clock, because when you talk about Verilog HDL, we want to discuss that we want to compute this Pi, Kp, Ki, Kd with in synchronism with a clock, because their computation time due to the proportional controller, the computation time of the integral controller and the computation time of the derivative controller may be different. But if we synchronize them with respect to clock, then all of them will be updated at one time. So, we will do clock synchronized PID controller. So, that is why here also you can use a clock to synchronize, and it is just a simple multiplication. If we do a digital PI controller, again this is a delay we have discussed. So, this represents an unit delay, and this can be realized by a register and which will be shifted by a clock. That means it is a clock driven register. and this can be realized. So, that you can see this part is the proportional part, where the proportional part is simply Kp into Ven, and we will be going to very log, then we will see this will be like a data flow modeling, which will be this. Then integral part will have ui of n minus 1 plus ki into Ve of n. So, this is there, and this delay is actually generated by this register. Similarly, if you go to so you can see it is a clock driven delay. That means whatever difference equation you are getting, that one cycle delay of this, that means this portion is nothing but delayed version of ui of n. That means this one is a delayed version, and this delay will happen with respect to clock. Although it is a 1 unit delay, but we also want to customize the age of updating as well as the age of delay. So, it is not completely like a transfer function. Similarly, for the PI controller, we can also generate. So, here what we need, this has to be Ven minus 1, this is Vn, because this is Ven, and this delay, that means this is a delayed version of this. So, this delay is again created by a register and a clock. So, this is a clock driven sampling. That means the update is happening with respect to clock. Okay. So, this is the proportional part, this is the integral part, and this is the derivative part, and the integral part is written like this, derivative part is written like this, and the overall implementation like this. This is the overall PID controller implementation using Matlab, and this is a screenshot, and I am going to show this entire implementation. So, you can see how can we implement in Matlab with the clock driven. So, this is our clock which will decide, that means you can say this is our event. Now, this clock can be uniform sampling, that means the clock frequency can be fixed, or this clock can invent a variable frequency clock, because we will extend the same approach. The same approach is applicable when you go to variable frequency modulation with event based sampling. So, the same block is applicable. What does it do? So, this block we have discussed about this A to D converter block. So, this is a triggered ADC, that means this ADC is not just a simple ADC. Here we will take the sample with respect to an event, that means the sampling will happen with respect to an event. And if you take any A to D converter, the clock, that means A to D converter, the conversion process start when a clock edge comes. So, that is why you are creating a virtually a similar A to D operation using Matlab simulation. So, this block is to create the error signal. Here the error signal is already generated, that means it is coming from the output block. That means if you are talking about, I will go to the complete diagram, but here I am just showing. If you have a discrete time error, then this error, suppose if you want to create Ven minus 1 from Ven, and this process is shown here. That means this, and this memory is needed at the start of the simulation, because if you start the simulation, since there is no value here, so that means it cannot start the simulation, it will show error, because it has to have something here. So, that is why the memory block is there, and I will go to the simulation show. So, this block is to perform this particular operation. That means it will, as if this block will generate just a Z inverse Ven, and it will generate Ven minus 1. Okay. What is this block? This block will generate Uin, and if it pass through this block, then it will generate Uin minus 1. So, this is another delayed block which will delay the integral term, and the proportional term is just a scaling factor. So, it is there. This is their integral block, you can see it, actually the whole block is integral block. This is the previous value. Okay, so if we, okay, So, I am just highlighting this is our ui n minus 1, this is our ven, and this particular signal is our uin, and this is going to the go to block. And this is the trigger pulse which is coming from, which is used in various blocks. You can see the trigger clock is used here, the trigger clock is used here. So, that means this is the clock which will synchronize all the update of this delay operation. Okay, and this actually is the realization of this PID controller. So, if we rub up this part, yeah, so if we, this block is the, so this whole block is realized by, that means this whole block is realized here. Okay. Now, again I am showing, so this is the what block we have discussed. This block is to, what is the task? If this is the block, input to this block is what? V error n, and output to this block is what? VE n minus 1, and it is driven by this external clock. Then what is this block? Again the input to this block is ui of n, and output to this block is ui of n minus 1. Okay, and then this is a complete PID controller that I have shown here. Okay, so that means now we will go to the Matlab to show that implementation of the PID controller. So, we are not going to use this transfer function because we have identified this way of implementation is not going to solve our purpose, because we want to sample with respect to time. So, you do not want to start sampling maybe at the start of simulation. So, we want to customize. Sometime in digital control we want to speed up the sampling process during transient. So, that means we need an adaptively varying sampling process during the runtime. The another requirement may be we want to use an event based sampling. So, to accommodate all this kind of customized sampling method, we should not use any by default transfer function block, we should realize using difference equation. So, here in this Matlab, this is a complete block diagram which I have demonstrated. Then in this block you can see, so first of all this is a power stage converter which you have explained multiple times. Then these are the input voltage, DCM enable, load step, everything is explained. Then this is the controller block, it takes the output voltage and the reference voltage and it generates the gate signal, and this is a sample point. If you go inside, this output voltage pass through an A to D converter. So, this is our A to D converter. So, you can see this is the A to D converter, and this A to D converter is driven by sampling process, is driven by a clock, and this clock we can delete this signal. That means now we can customize the sample edge, okay, or we can use any other clock which is respect to the event, and that we will be discussing in the subsequent class. Then this is our sample voltage, that means this is our sample voltage, you can see it is going to output, that means we can see in the scope. Then this is our reference voltage minus the sample voltage. So, this is the error sample error voltage, and which is going to a digital controller. Now, the controller computation will be carried out with respect to this clock. That means it may not be the same clock of ADC will be used for computation, because even if you send the start command of the sampling command, and that sampling process will take time, because ADC conversions there is a finite time for ADC conversion time. Once the data is ready and it passed through the error, then only the controller can start computing, otherwise it will take the wrong data. So, this clock has to be delayed. So, this clock has to be delayed with respect to this clock, so that the difference can accommodate the ADC conversion time. Now, if we go inside this controller, what is there? Rest of the blocks are same. That means you can see this modulator is a trailing edge modulator with respect to the switching frequency clock. This is a sawtooth waveform. You can also add a quantized block here, but objective here, if you go inside, that we have explained. So, this block is to generate the delay of the error voltage, that means VEN, this block will generate VEN minus 1. Similarly, this block the same, exactly same block, but it is used to generate uin from uin to uin minus 1, because if we talk about the integral, it is an incremental integral process discrete time, where ui of n is equal to ui of n minus 1 plus ki into the error voltage. So, this block is generating that previous term that is generated and it is used here. This block is the trigger pulse and we are taking from outside. So, because as I said that controller computation will happen with respect to a clock, and number 2 is this clock. So, this is the port and this clock actually is given here and here. That means all the operation like a delayed operation etc. is happening with respect to this clock. And finally, this is the overall implementation of the PID controller, where this is the proportional part, this part is the, if you take this part, overall is the integral part, where this is your ui of n and this part is the derivative part, and all are added together to generate the PID controller. Okay? And if we go to the simulation, that means that this is the simulation. Now, I have shown in the previous class. So, if you set Kp, Ki some value, this we have taken in the analog domain. Then I have also discussed in the last class that how to convert into digital domain. That means the discrete time proportional gains remain same. The integral gain is nothing but analog integral gain multiplied by the sampling time, and the derivative gain in digital domain is nothing but continuous time derivative gain divided by the sampling time. By that way we have run, and if you run the simulation, so I am just carrying out a load transient of a digitally voltage mode converter, and this is the one which is shown. So, you can see that this is the operation. Now, in this plot, if I go to plot Simulink, and if we want to plot that means if we want to see the sample point. So, let me check that whatever we are capturing, it is the third channel. So, what is the third channel here? So, the third channel is the sample point. Okay. So, let us go to the simulation and now run this plot simulation. So, we have the capture, and you can see the red one indicate the sample value, and we want to show that now this is under steady state. Now, during transient, if you see that the switching point and sampling point can be even shifted. So, here we have not used any delay, but if you use any delay, that means we have the provision to adjust delay. So, let us go back to our code, because here we have used TS to be this, but suppose if we want to use this TS which is the delay, and maybe we can just use a 0.9, let us run it. We are just delaying the so let me check. Now, we have applied a delayed version of this delay. Now, you can see we are sampling earlier than switching, that means first sampling is happening. So, if you look at one cycle during transient, let us say this transient, if you look at here, switching point is happening here, but the sampling point is happening here. That means, if we just zoom in, first it is sampling here and then switching, sampling here and then switching. So, we can customize this sampling point. Okay. So, that means we have learned that we can sample in the controller either by event clock or even adjustment. We can adjust the age of sampling with respect to the switching clock by using difference equation, and by using this clock driven difference equation, where we can implement any type of controller, PID, PI, anything. So, in summary, we have learned step by step custom Matlab model development for digital controller, then digital control implementation using difference equation, and Matlab model for digital voltage mode control. And we will just take once again in the next lecture the digital voltage mode control implementation, overall implementation. With that, I want to finish it here. Thank you very much.